it's meant to highlight um, one way of addressing the problem of the disturbance term being correlated with one of the explanatory variables. This problem of endogeneity arises if we have omitted variables, if we have simultaneity, and if we have measurement problems. Today we'll start with another topic, the systems of equations. I'll be focusing for the systems of equation on seemingly unrelated regression. Okay. Though I'll start with system OLS, then go to system GLS estimation. After the systems of equations, we'll go to simultaneous equations, then move to panel data approaches. Okay. Well, Woolridge treats the panel data approaches using the framework of systems of equations. Sometimes I find it confusing, so it depends later on if I can find a more simpler and intuitive approach to panel data regressions. Okay. Okay. Any questions? Okay. So I have obtained Jaden's permission for you to attend also his Saturday classes. So you have already the link, the Zoom link to attend. Okay. Okay, so I'll start the share screen. Okay. Okay, I will redo the detailed course outline. So I'm just going by topic. So I will note it as topic 1, topic 2. So for system of equations, there are various subtopics, but I'll put them all under topic 2. Okay. An example of systems of equations is the seemingly unrelated regression model. We assume random sampling of units from a well-defined population. Therefore, for sure, you sample several different response variables along with explanatory variables. For the population model, note that this is a population model. We have G equations, so we have G different response variables, y sub 1, y sub 2, down to y sub g, okay? For each equation, we then have explanatory variables. So we have the x sub g. So for the first equation, we have x sub 1 contains the explanatory variables for y sub 1. X sub 2 contains the explanatory variables for y sub 2, and so on to the last equation, x sub g contains the explanatory variables for y sub g. Okay. Here, the x sub g's can be different across equations. We consider now these beta sub g's to be unrestricted across equations. That doesn't make the problem of estimation so interesting, but for now, I just want to highlight the assumptions and how we would modify the assumptions later on. For now, we consider the beta sub g's are unrestricted across equations. Okay. That's quite a strong assumption. In some economic applications, then um, our findings might not hold because sometimes economic theory imposes restrictions on the model, and also sometimes for identification you want to put some restrictions. um, okay, so example for restrictions across equations for the beta sub j's would be, for example, um, the assumptions of symmetry and convexity in consumer theory or producer theory. If you take into account those assu- assumptions on the economic theory side, then you would be imposing cross equation restrictions on the betas. Okay. So take note of this G equation model for the seemingly unrelated regression model. So it's quite simple. It's very similar to what we had for instrumental variables, except that now we have a stack of these equations. Okay. Let us look at assumptions about the exogeneity of the explanatory variables. As you mentioned before, the exogeneity of the explanatory variables has something to do with the relationship of the explanatory variables with the disturbance terms. Okay. One possibility is we have the conditional mean assumption. The expected value of u sub g given x sub g is equal to 0, g going from 1 to g. Okay. Note that we have, for this assumption, we would have g of these equations, one for each equation. But note that for each equation, we're just imposing the condition on the relationship between the disturbance term and the explanatory variable for that equation. Since we have big G or uppercase G equations, then we have uppercase G um, equations for this assumption. Okay. If this assumption holds, then what does this imply? Then if you get the conditional mean of y sub g given x sub g, okay, then you have to take the expected value of the right-hand side conditional on x sub g. Then you would just pick up the first term. So it would be x sub g, beta sub g, g going from 1 to g. Okay. So that means that the conditional mean of g, of y sub g, conditional on x sub g, is just x sub g, beta sub g. Okay. Again, those the boldface notation I have means that I'm dealing with vectors or matrices. Okay. If they're not in boldface, then they are just scalars. Another possibility is having this assumption, which is really a weaker condition. The expected value of x transpose g, u sub g is equal to 0. Okay, which means that the covariance of x sub g and u sub g is equal to 0. Okay. Note that neither 1 and 2 restricts the relationship between x sub h and u sub g for g not equal to h. So if you have two equations, okay. So if you have two equations, for example, the second equation and the last equation, this assumption does not impose any restriction on the relationship between X sub 2 and U sub G. Okay? It just imposes the relationship between X sub 2 and the disturbance term within that um, equation. Similarly, we have no restriction on the relationship between X sub G and U sub 2. We're just imposing the assumption on the relationship between X sub G and the disturbance term in that equation. Okay, is that clear? Also,
Question lang po.
yeah,
Um,
sure.
are we dealing lang po ba dito with one response variable for this SOR? So,
Or,
isang response variable lang po to that
no,
has multiple values.
um, well, um, you y sub 1, y sub 2, y sub g are different response variables. We will have an example later. Suppose you have you're looking at compensation of workers, and the compensation can take various forms. It can be in terms of salary or and wages, can be
Mhm.
in terms of pension, health, or health benefits. You have three possible forms of compensation, and on the left hand side, then you would have three different response variables.
Okay po, thank you po.
Okay, or if you have let's say consumption of five goods, then you have one equation per kind of good. Okay, so suppose y sub 1 is consumption of food, y sub 2 consumption of clothing, y sub g consumption of services, and so on. Okay.
Okay. So, just to clarify lang po, so pang y sub 1 po, this is a vector po, a k by 1 vector po ba to? Or a
Y sub
scalar?
1 is one by one.
Ah,
Note that this is just a population model. So when it comes to when you have actual data, when you do random sampling, and suppose you have 100 observations, then you would have 100 values of y sub 1, right?
okay. Okay po. Okay, gets. Thank you, ma'am.
Then 100 values of y sub 2, and so on. Okay, yeah. It's good you're asking now because this can be the notation can be confusing. That's why I want to go through these sections, though you would have touched on these concepts before, except that as I said before, as you shift from one book to another, sometimes the notation becomes messy. Okay. Okay, so in contrast to the single equation model, we just have one y. As in the instrumental variable model we had, G is equal to 1, big G is equal to 1. Okay. Okay, going back to these two assumptions, um, note that the first assumption is in terms of conditional mean. So this is the zero conditional mean assumption. We have zero at the right hand side. The second assumption says that the covariance of u sub g and the explanatory variables in that equation is zero. Okay, and this is weaker. Actually, if the if the first assumption holds, that is equation one holds, then that implies that equation two holds. Okay, um, that's why I want you to go um, to the concept of mean independence. I think Charles is giving you an exercise on mean independence. Um, we have three kinds of possible relationships. Well, the strongest is um, the X sub G's are independent of the disturbance term. Okay, but we're not assuming that here. Okay. The second is we have conditional mean independence. So we have it in this form. Okay. But this conditional mean independence is weaker than full independence. And the alternative weaker assumption here is um, uh, less restrictive, but two does not imply one. One implies two, but two does not imply one. Okay, so a stronger, going back to that, okay, so independence is a higher level of a stronger assumption, but we do not assume that here. Okay, a stronger assumption, implicitly or explicitly maintained by most sure analysis, is the following: the expected value of u sub g given the explanatory variables in all the equations is zero. G going from 1 to uppercase G. So this says that, going back to our model here, okay, um, for this first set, for this assumption, we just required the expected value of u sub 1 given x sub 1 is equal to 0. Okay, we're not imposing any restriction on the relationship between u sub 1, x sub 2 down to x sub g. But with this assumption, which is stronger, we are assuming that u sub 1, the expected value of u sub 1, given all these x's, including the x's in the other equations, is equal to 0. Okay. Similarly, for u sub 2, the expected value of u sub 2 given all the x's is equal to 0. Okay. And so on. The disturbance term for the last equation given all the x's in all equations is equal to 0. So this is stronger. Okay. So if you apply this assumption to the model, then if we get the expected value of y sub g given x sub 1 down to x sub g, okay, so you apply it here, the expected value of, say, y sub g given all these x's would be the expected value of this given all the x's plus the expected value of u sub 1 given all the x's. Okay, so what do you get? Okay, um, you get the expected value of y sub g given x sub g is equal to x sub g beta g, g going from 1 to g. Okay, um, I'll just go through this. Hmm. Okay, because Woolridge does a lot of this kind of expectations. Okay, I'll use the whiteboard. Okay. Okay, so we have the expected value of y sub g given x sub 1, x sub 2 down to x sub g. Okay. So if you apply it to the model, okay, so that is the expected value of what is y sub g. Y sub g is x sub g beta sub g plus u sub g, okay, conditional on x sub 1, x sub 2 down to x sub g, okay. So to get this expectation, you just distribute the expectation operator. So you get the expected value of x sub g beta g given x sub 1 down to x sub g plus the expected value of u sub g given x sub 1 down to x sub g capital. This is x sub g. Okay. But by assumption, we have this is equal to 0. Okay. So we get the expected value of this, but we're fixing the x's, and beta sub g is just a vector of parameters. So this would be x sub g beta g. Okay. Is that clear? Okay. Um, this is just a trick repeatedly used here in Woolridge book. Okay. So what does that mean? Okay. This means that x sub h for h the not equal to g, x sub h um, so we're looking at two different equations, the h equation and the gth equation. If x sub h includes elements not in xg, then those elements of xh are assumed to have no partial effect on the expected value of y sub g once x sub g is controlled for. Okay, so suppose you have um, um, so suppose for you're looking at x sub 1 and the last equation. Okay, suppose the first equation has x sub 1 that has an explanatory variable not included in the last equation. So suppose x sub x sub 1 includes the has in x sub 1 the price of good one, but the price of good one is not included in x sub g. It does not appear in the last equation. So that means that the price of good one has no effect on y sub g once you have controlled for x sub g. Okay. So you have this. Okay. So note that the expected value of y sub g depends only on the, the x's in that equation. Okay? And that is a pretty strong assumption. Well, we don't really need the disturbance term to be conditional on the x's once we have this, because we get this result only with, we already get this result with this much weaker condition, the conditional mean independence assumption. Okay. Okay, so just go through all these assumptions on oxygeneity. Um, so there are four kinds we had here. three kinds. Okay. So we have the condition, zero conditional mean assumption, the weaker condition that the covariance is zero, and this stronger assumption given by equation 3. Okay. Check also if x sub g is equal to x sub h for all g and h, there is no difference between 1 and 3. That is, suppose all this x sub 1 is the same as x sub 2, um, which is also equal to x sub 3 down to x sub g. Then this conditional mean independence assumption, conditional only on x sub g, would also be identical to this third equation. Well, it makes sense because all the x's are identical, right? All these vectors are identical. So you just need one. You might as well just have x sub g, okay? Okay, so this is the example, um, so example of a seemingly unrelated regression model. Suppose each worker in a population receives three kinds of compensation: wage, pension, and health benefits. Okay. And in this case, we have the same set of explanatory variables on the right-hand side: educational attainment, tenure, age, and union. The unit of observation here is workers from the target population. Okay. Here we have three response variables. Therefore, G is equal to 3. This is a special case where x sub G is equal to all to x sub H for all G and H. Okay. Yeah. Okay. In practice, though, you might have x sub G is equal to x sub H for all G and H, but then we are assuming for now that we have no cross equation restrictions on the betas. But once you have cross equation restriction on the betas, then some of our results would not hold. Okay. Excuse me. We'll first do system OLS estimation. Okay, so you suppose you get one unit from the population. Okay. Okay. Usually, our objective is to estimate these betas. Okay. The betas in the first equation, the betas in the second equation, the betas in the last equation. Or in this model, we want to estimate these betas. And note that the betas can differ across equations, right? The intercepts can vary per equation. The coefficient of the education variable can vary depending on the equation. Okay, that means we're allowing for education to affect wage differently compared to the effect of education on pension benefits or of education on health. So we're allowing different marginal effects of education on the dependent variable. Suppose we have a random draw from the population So we have one observation, say observation I, okay? This is a unit specific observation as against the full data matrices, which we would have later on. So we use the subscript I to denote that is for a specific draw from the population, okay? So we have y sub I is equal to x sub I beta plus u sub I, okay? Y sub I is g by 1. So for example, for this model, we would have the vector y sub I would be a 3 by 1 vector for that worker, for a specific worker. Okay. So we have his observed wage, observed pension benefit, observed health for a specific worker in our sample. Okay. Then we have x sub I beta plus u sub I. X sub I now would be g by k. Okay. It would be helpful first to specify beta. Okay. So beta is k by 1. Okay. In this model, how many parameters are we estimating? Per equation, we have 5 parameters, right? Five parameters we are estimating. Um, for the whole system, we have 15 parameters we are estimating, 5 times 3, assuming we have no cross equation constraints. Okay. So K here would be K by 1. So list down first the beta matrix, then specify the Xi matrix. Okay. So first have the coefficients for the first equation, then stack the coefficients for the second equation, then stack the coefficients for the third equation. Then specify the um, the corresponding X sub I matrix. So the X sub I matrix would be your matrix of explanatory variables. Okay, so this would be G by K. Okay, so you have G equations. So G will be 3. And for each row, then you would have for each row of the X vector, then you would have 1, education, tenure, age, union, data for that observation. For the second row, you have 1 because you have the intercept, then you repeat education, tenure, and so on. Okay. Okay. Well, to do that, well, that's not exactly true. You have to you have to match it to the coefficient vector for proper specification of the x sub i's. Okay. Okay. So note that x sub I is g by k, beta is k by 1. So you would have the product is g by 1, and which is also the dimension of y sub I and the u vector. So the u vector would be u sub I1, u sub I2, u sub I3. There's an error here. This should be 3. Okay, for your observed data, okay, so you have, if you have n for your sample size. So you have x sub sub I going from 1 to n. So you have an x sub y sub I. Those are your observed values from the random sample. Okay. Okay, y sub I is a vector. It is g by 1. Okay, so I just express it here as a row, the transpose of a row vector. So you actually have a g by 1 vector. So you note that you have y sub I1, y sub I2, down to y sub ig. Okay. Then similarly for u sub I, you have u sub I1, u sub I2, down to u sub ig. Okay. These should be column vectors once you've gotten the transpose. Okay. So specify first the beta vector. Okay, so you have the beta for the betas for the first equation, the betas for the second equation, down to the betas for the last equation. If you have different number of explanatory variables across equations, okay, then if k sub g is the number of explanatory variables in the equation, including the interceptor, then you would have k sub 1 plus k sub 2 down to k sub g is equal to k. Okay. So once you have written that, okay, so I have it here. K would be k sub 1, k sub 2 down to k sub g. Okay. Now this is what I mean by specifying correctly the x sub I vector. Note that what is the dimension of the x sub I vector? The x sub I vector would be g by k. Okay. Note that I have everything here in boldface, like what is the dimension of x sub I1? That would be 1 by k sub 1. Okay. And this would be 1 by k sub 2, this 1 by k sub 3 down to 1 by k sub g. So the sum of the columns would be k. Okay. Okay. I didn't bother writing the whole matrix here. I'll see. Okay, so I'll shift again to the whiteboard. Okay, so we have x sub I. Mhm. No, I want to show something else later. Mm. Okay, we have okay, so this is the observed values for the explanatory variables for the ith unit. Okay, so we would have x sub I1, 0, 0, down to 0. Okay, excuse me. For the second row, this would be 0, x sub I2, 0, 0. For the third row, it would be 0, 0, x sub I3, down to 0. And so on to the last equation, you would have 0, 0, 0, and you would have x sub I g. Okay. So the number of columns here would be k sub 1. The number of columns here is k sub 2. Here k sub 3. Here k sub g. So the total would be k. The number of columns would be k. But how many rows would you have? You would have g. Okay. So the dimension of this matrix is g by k. Okay. Let me then go to what is then x sub I transpose x sub I. Okay. Okay. How do you call the x sub I matrix? Did you describe this as black diagonal in your earlier math econ classes?
No po. No po.
Anyway, what is x sub I transpose x sub I? Okay, so we have x sub I transpose x sub I. So you're multiplying a k by g matrix by a g by k matrix. Therefore, you should get a k by k matrix. Okay. Okay, but what should you get here? Okay, so you should be getting x sub I1 transpose x sub I1 along the diagonals, x sub I2 transpose x sub I2, x sub I3 transpose x sub I3, and so on to x sub IG transpose x sub IG. Okay, and then zeros elsewhere. Okay, so loosely speaking, when you have x sub I transpose x sub I, then you are just um, getting sort of sum of squares. Um, x sub ik is 1 by k1. So x sub I1 transpose x sub I1 would be what?
1 by 1. Okay. Anong
1 by k1.
hindi,
So it would be k1 by k1, right?
yeah, yeah.
Because you have x sub I transpose. So it's k1 by 1 times x sub 1. Okay. Okay. So we get the right dimension because if you sum k sub 1 for the rows, k sub 1 rows, k sub 2 rows, you would get a total of k rows, and for the columns also k. Okay. Okay. We will be using this matrix later on. You can verify. Okay. I'll go back to the lecture. Um, okay. Okay, so our objective is to estimate the population parameter beta. Okay. We look at the concept of consistency. Well, we really first derive what is the system OLS estimator. Excuse me. Okay. Okay. Um, well, the system OLS estimator would have the property that it is consistent. When we talk about consistency, it is a large sample property. Um, Therefore, here we're looking at what happens when we collect more and more data on units. So n increases. Okay. Okay. Let us have the two assumptions we'll have for the system OLS estimation. Okay. So here we're taking the weaker assumption, the expected value of x sub I transpose u sub I is equal to 0. Okay. This is the weakest possible assumption without um, having to use the instrumental variables. Okay. So here we're assuming that the x's are uncorrelated with the disturbances. To see what this means, um, write out this expression. Oh, actually, I have it here. Okay. So we have x sub I transpose u sub I. If you write out x sub I transpose u sub I, you would get this. Um, you would get this expression. Okay. So this would actually be a G by 1 matrix or vector. Okay, as a stronger assumption is the conditional mean assumption, which would just imply the previous this assumption. Okay, a stronger assumption would be independence between u sub I and x sub I. But for now, for this section, we are assuming the weaker assumption. Note that if you then get the expected value of each of these, then you would have G conditions, the expected value of x sub I transpose G, U sub IG is equal to 0. Okay. Okay, that means that there's zero covariance between the explanatory variables and the disturbance term in a given equation. Okay, we're not looking. Note that this does not restrict the relationship between u sub ig and the covariates in other equations. Okay, because you just have the same equation here. You just have x sub ig. Okay. Okay, that can be important when we go to inference also. The second assumption we have is the rank condition. The rank of x sub I transpose x sub I is equal to k. So if you look at the matrix I had earlier on the whiteboard, that this assumption is the same as assuming that the rank of each of those black diagonal matrices, those are k sub g by k sub g matrices, um, are of full rank. Okay. So as an exercise, well, I've already given you anyway the matrix. Verify how this expression came from this. They are the same assumption. These are just equivalent expressions. It's just that this is in matrix form. This one is in full matrix form. This one is in terms of each equation. Okay, the rank condition then is that the single equation OLS rank condition holds for each equation. This was our assumption. Why did we have this assumption? for each equation, so that we can get um, the inverse. Well, if you have OLS and the model y is equal to x beta plus u, then the beta hat OLS is just x transpose x inverse x transpose y. So for x transpose x inverse to exist, we need this rank condition. Okay, so let's derive the system OLS estimator. Okay, let's work on the population. And here we will just use these two assumptions, the exogeneity assumption and the rank condition. Okay, so the first assumption, the exogeneity assumption is this. Okay? And I have just rewritten it here. Okay. In the next step, I re-express u sub I, and for that I use the model y sub I is equal to x sub I beta plus u sub I. Okay, therefore u sub I is y sub I minus x sub I beta. Well, we have that here. Here, okay. So to get an expression for u sub I, you just have y sub I minus x sub I beta is equal to u sub I. We have it here. Then let's distribute the expectation operator. Okay, so first you're multiplying these two terms. So you have x transpose y sub I and x transpose x sub I beta, but you have a minus sign. Then distribute the expectation operator. So you get this. Okay. Then looking at this expression, beta is a vector of parameters and that is fixed. So you can bring it outside the expectation operator. So you have the vector beta here. Okay, so be careful here. You cannot put beta before this expectation operator. You would be you will be messing up the dimensions for matrix multiplication. Okay. From this equation, okay, let's have beta, the expression for beta on the left-hand side. So we get this is equal to the expected value of x sub I transpose y sub I. Okay. Then where do we need the second assumption? The second assumption, the rank condition ensures that this inverse function exists. Okay. So beta is equal to the inverse of the expected value of x sub I transpose xi times the expected value of xi transpose y sub I. Okay. Note that this is all our note that this describe all the equations here describe the population. So beta is the population unknown parameter vector, and we have expectations. For you to get expectations, you would need data on the whole population. Okay. How do we get the system OLS estimator? Okay, we denote the system OLS estimator as beta hat sub SOLS. Okay, so we have hat to denote that is an estimator, and the way of getting the estimator is by system OLS. Okay. So here we just use um, the result that the sample means are consistent estimators of the population means. Okay. The population mean being given by this expectation operator. Okay. Okay, so for the expectation of x sub I transpose xi, what we have are sample observations going from 1 to n of x sub I transpose x sub I. So we have observed values of this for n sample units in the random sample. But we're getting the mean, that's why we're dividing by n. Okay. So this is the sample mean associated with this population mean. Okay. Then we have the inverse. We'll be getting PLM, so it does not, um, because of the nature of PLM operators, then we can just get the sample mean of the associated sample mean of this. Okay. Okay. Similarly, for the expected value of x sub I transpose y sub I, we just have this n observed values of x sub I transpose y sub I. We sum those, divide by n. So this is the sample mean of x sub I transpose y sub I. And that is the estimator of this expected value. This is a consistent, this sample mean is a consistent estimator of this population mean by the nature of um, using the weak law of large numbers. Okay. Well, you can further rewrite this as x transpose x inverse x transpose y, where x is ng by k, y is ng by 1. So for this x, you just stack up the observations. That's why it's ng, the number of rows is ng. And for y, you also just stack up the observations. That's why you also have ng rows. Okay, using this notation, then you get x transpose x inverse x transpose y, a formula that is very similar to what we have for ordinary least squares for a single equation. Okay, then we have the following theorem under the two assumptions, SOLS1, exogeneity, SOLS2, the rank condition. System OLS on a random sample is consistent. That is, prelim of beta hat of the beta hat would be beta. Actually, it's easy to establish because you just get the prelim of this and you should get this. Okay. Okay. In the sure case, you can work it out by expanding this. In the sure case, the system OLS estimator is ordinary least squares equation by equation. Okay. So beta hat G is just the OLS estimator for equation G. Okay. Okay. What are the sufficient conditions for the consistency of OLS for equation G with random sampling? Or another way is just to write the assumptions when uppercase G is equal to 1. Then that is what would be your sufficient conditions for the consistency of OLS. Okay. Here I know too, when parameters are restricted across equations, then system OLS is not OLS equation by equation. Okay. Okay, so for this section then, what we did was lay out the assumptions for system OLS. And from those system OLS conditions, okay, so we have two assumptions, exogeneity and the rank condition. From those assumptions, when then we're able to get an expression for beta in terms of the population moments. Okay. Then we got a consistent estimator, beta hat, given by this formula. Okay. In econometrics, we're not just interested in um, finding the value of the estimator or getting an estimate. We are also interested in test of hypothesis or confidence intervals also. For that, we appeal to large sample theory. Once you get outside the framework of the Gauss-Markov theorem, um, you usually have to appeal to large sample theory. Okay. Okay. Once you get all these other complications, you do not get nice small sample properties, but you appeal to the asymptotic properties. Okay. So we have, let's look at the asymptotic normality of our estimator and how we use that in inference. Okay, so for ease of notation, let's denote the system OLS estimator as simply beta hat. Okay. Okay. Then we get the expression for n to the 1/2 beta hat minus beta. So where do you get this? Um, n to the 1/2 beta hat minus beta. Okay, so you, okay, note that this is our expression, right? So what you do is just substitute the model for y sub I. You have x sub I transpose beta plus u sub I. Okay. So for, note that I don't have a y sub I here. I only have an expression in terms of u sub I. So to do that, substitute the model equation for y sub I, which is x sub I beta plus u sub I. And that would simplify to this expression. Okay. Okay, that is for beta hat. Well, you can factor out some term that would be equal to beta. So you would have beta hat minus beta, and you would be left with this. Okay. This, you just use the usual trick for showing unbiasedness or consistency. Okay. Okay, by the central limit theorem for independently and identically distributed random vectors, we have n minus 1/2, okay, this expression, n to the minus 1/2 the summation of x sub I transpose u sub I, this would have, this would converge in distribution to the normal distribution with mean 0, because the asymptotic mean of the u sub I should be 0, and variance covariance matrix, which I denote by B. So B is the variance of x sub I transpose u sub I. But the variance of x sub I transpose u sub I is the expected value of x sub I transpose u sub I transpose x sub I. Okay, let's denote, okay, so we have defined the B matrix is the variance covariance matrix of this term. Okay. And then let us have A as the expected value of x sub I transpose x sub I. Okay. Note again that this pertains to the population because we have unexpected value. Okay. We do not use the expected value when we're using only sample data. Okay. Because for sample data, we just have a sample of observations from the population. We do not have data on the whole population. Okay. So let us re-express this n to the 1/2 beta hat minus beta, which is this. Okay. Okay. So what I did was, okay, so we have this term. Okay, so we have n minus 1, the summation of x sub I transpose xi inverse, which is this, multiplied by this expression. Okay. So this multiplied by this gives us this. Okay. Okay. And then I add and subtract the same term. Okay. So for the first, so I have A inverse, the inverse of this, n minus 1/2, the sum of x sub I transpose u sub I, this. So if I'm adding this, then I'm subtracting here. Okay. Then if you look at these last two, this second term, okay, you have this first term is little op1, it converges in probability to 0. And this other term is big op1, which means it is bounded in probability. Okay. So let's define bounded in probability. I'll just have this in here. This is a definition, so it's an if and only if statement. A sequence of random variables x sub n is bounded in probability if and only for every epsilon greater than 0, there exists a b sub epsilon less than infinity and an integer n sub epsilon such that the probability that the absolute value of the random variable is greater than b sub epsilon is less than epsilon for all n greater than equal to n sub epsilon. Okay. So intuitively, that means that the value of the random variable is bounded. If you have a sufficiently large sample size, then the probability that the absolute value of x sub n is greater than that number b associated with epsilon is less than epsilon. Okay. Okay. That is the definition of big O P1. Okay. Last time we have little PO1, which means that the random variable converges in probability to 0. We have this lemma. Suppose the random variable converges to some real number A in probability, then that random variable is bounded in probability. Again, intuitively, that makes sense. Okay. If the series of random variables um, converges in probability to some real number, then it is bounded. Okay. Okay. Then we have this lemma. Let C sub n is equal to 1 to 2, 1, and so on, be a sequence of J by K matrices such that Z sub n, these are matrices, converge in probability to 0. Okay. So the entries in that Z sub n matrix tend towards to 0 as you get more sample observations. And let x sub n, now this is a vector. Um, this is a this set is a sequence of j by 1 random vectors such that the vectors are big O P1. So they are bounded above. Okay. But if you get the product of C sub n and x sub n, then that random variable would be little OP1 or converge in probability to 0. Okay. So going back to this expression, the first expression in brackets converges in probability to 0. This is the second expression here is bounded in probability. So the product of these two would be little OP1 or converge in probability. So as n approaches infinity, the product would approach 0. Therefore, if n is sufficiently large, then we're just left with the first term on the right-hand side. So we're just left with this term. Okay. Let's rewrite then this expression on the left-hand side. Note that this random variable, why is it a random variable? It's a random variable because beta hat is a random variable. Beta hat would depend on the sample observations. Okay. Therefore, n to the 1/2 beta hat minus beta here would converge in distribution to the normal distribution using the central limit theorem with mean 0, asymptotic mean 0. The mean of this, because of this, the mean would be 0. The asymptotic mean would be 0. And we have the variance covariance matrix A inverse B, A inverse. Okay. So we have defined B. Okay. That is, B is this. And we have defined A. Okay, note that the right-hand side is in terms of the population again. You have A is the expected value of X sub I transpose X sub I. B is the variance of X sub I transpose U sub I. So we need to get estimators using our sample data for A and B because they would be unknown. Okay. So we use the same trick. We use the sample mean counterparts. Okay, so for A hat, we get the sum of X sub I transpose X sub I going from 1 to n, divided by n. So that is the sample mean of X sub I transpose of the observed X sub I transpose X sub I. And we have n observations in the data. Okay. An estimator then of A is this A hat. Okay. We can calculate A hat based on sample data. Okay. How about for B? Again, B pertains to the population, is the variance in the population of X sub I transpose U sub I. Okay. And that would just be the expected value of X sub I transpose U sub I transpose X sub I. Um, so this is just a generalization of in matrix form of let's say you have the variance of a single variable x. It is equal to the expected value of x squared minus the mean of x squared. Well, the mean of this x sub I transpose u sub I is 0. The asymptotic mean is 0. And for the variance, then you get the expected x squared. This would be the counterpart. So what? So this is what we would like to estimate. Okay. So from our sample data, we can estimate the sum of x sub I hat transpose u sub I hat, q sub I hat transpose x sub I. Okay. What is this u sub I hat? U sub I hat would be the OLS residuals. Okay. So that is y sub I minus x sub I beta hat. And the sample counterpart would have this summation divided by n minus k. Okay. Since we're appealing to large sample theory, it won't make much difference if you use n, simply n, instead of n minus k. Okay. So we have estimators for A hat and B hat. So we have an estimator for this variance covariance matrix. Okay. Okay. We note that beta hat is a fully robust estimator of B, okay, valid under the two assumptions and without any second moment assumption about on U sub I. Okay. 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 Later on, you will see why it is robust. Okay. Okay. So what would be the estimator for the asymptotic variance of beta hat? So if you manipulate this expression and substitute the estimators, then you would get the asymptotic variance of beta hat is equal to this. Note that the right-hand side just involves calculating values um, from the sample. So the x sub i's that are observed values, you have data on that. what you have to estimate before you get asymptotic variance is u sub I hat, the residual, okay? And but you can calculate it using this, okay? So that is the asymptotic variance of beta hat. So let us denote that by the matrix V hat, or the, the estimator for the variance of beta hat. Okay. Note that the asymptotic variance of beta hat allows arbitrary covariances in the errors across the different equations. Okay. Different variances, and allows all conditional variances and covariances to be unknown functions of x sub I. Okay. Okay, so this is asymptotic of variance of beta hat. Note that our assumption only that we use are the two assumptions on the disturbances, the exogeneity assumption and the rank condition assumption. Therefore, we did not impose any other restriction. Therefore, the estimator for the asymptotic variance allows arbitrary covariances in the errors across the different equations. That is, this allows for u sub 1 to be correlated with u sub 2, or u sub 2 correlated with u sub g. We did not impose any restriction on the covariances of of the disturbances across equations. Okay. Neither they can also have different variances. The variance of u sub 1 can be different from the variance of u sub 2, and which can also be different from the variance of u sub g. So similar to the single equation context, you can have a correlation among the disturbances in the across equations, and also you can have different variances of the disturbances. So in a way, instead of heteroscedasticity, unequal variances across observations, you have unequal variances of the disturbances across equations. Okay. And we allow all conditional variances and covariances to be unknown functions of x sub I. Okay. So the variances, covariances of these can be functions of x sub I. We did not impose any restriction. Okay, so is in that sense that you have the asymptotic variance estimator is robust. Okay. Now, how do we go about testing? Okay, so if you're just testing for significance of a coefficient or a linear combination of the coefficients, then you can use the usual t statistics. However, use the asymptotic standard errors from this formula. Okay, so obtain the standard errors from 6 v hat to construct large sample t statistics, and we know if n is sufficiently large, the t distribution approaches the normal distribution. So you can also use the standard normal distribution. What if you have q linear restrictions? Well, the usual notation is you have R beta is equal to R. You have Q restrictions, so R is Q by K. k is the number of parameters, um, you would want the restrictions to be less than or equal to the number of parameters. Okay. Otherwise, if this is violated, um, then you would have an over-identified set of restrictions. Okay, R is Q by 1. Okay, okay, so R is Q by K, beta is K by 1. So you get Q by 1 at the left-hand side. R here is also Q by 1. Okay, what is often used, you would see this in the computer programs, is the Wald statistic. So this is R beta hat minus R transpose R v hat R transpose inverse R beta hat minus R. Did you take the large sample test, likelihood ratio test, um, while test and Lagrange multiplier test before?
No, ma'am. Or we're not. We don't. I don't think so.
Okay. Anyway, those are the three common tests when you're using um, when you're using um, large sample theory. Okay. So the F and the T test, they're usually for there are small sample tests. Okay. This is asymptotically distributed as chi-square with q degrees of freedom if the null hypothesis is true. Okay. Note that the test statistic is derived under the assumption that the null hypothesis is true. If the null hypothesis is true, then this test statistic would be asymptotically distributed as chi-square under degree with q degrees of freedom. Okay, so you would have q degrees of freedom here. So if you look at this Wald test statistic, you are summing the squares of q standard normal random variables. Okay. That is why you have a chi-square distributed um, random variable W. Okay. Oh, okay, so I'll stop here. So it's really not so interesting for our system OLS now because we don't have cross equation constraints. Probably the interesting part is this asymptotic variance of the system OLS estimator. Also, note that here we went right to showing the consistency of the system OLS. In general, the system OLS is not unbiased under the first two assumptions. Okay, under these two assumptions. Okay, you need a stronger assumption for system OLS to be unbiased. Okay. Unbiasedness is a small sample property. We just looked at consistency, a large sample property, and all we needed was um, these assumptions. Okay. Okay, so I just worked through it so you would be familiar with the framework. Um, for the rest of Woolrich book, it is just modifying these assumptions, but the tricks are more or less the same. Okay, so on Tuesday, I'll go through system GLS and sample of the seemingly unrelated regression uh, application. Okay. Okay. So maybe uh, um, we'll see if we can finish a seemingly unrelated regression where in the original timetable, I should have taken simultaneous equations uh, by next week. So um, we're behind our original timetable. Okay. Okay, so that's it for today. So I'll see you Thursday. Do you have questions? Okay. So just flat through Woodridge book. I know it's so tedious going through Woodridge book, and also his approach is a bit different from earlier books in econometrics, but more modern approaches in econometrics use the approach of Woodridge. Okay. Okay. Um, well, the next section on GLS would be probably more interesting. Okay. So I hope to finish GLS and get to the sure application. Okay. I'll skip IV estimation in the context of systems of equations. Okay. Maybe we'll just use it as needed in simultaneous equation models. Okay. Okay, no questions.
Yan naman pa.
Yeah. So, Charles, you gave them the problem set, no? Not yet.
Ano ma'am, yung for IV due today, wala pang bago.
Okay. The one, what you gave me was for 106, right?
Yes, yes.
Nalilito na ako. Okay. Okay. So, just plug on. Yeah. And play with data. Okay. So, see you Tuesday and have a nice weekend. But do not go out too much kasi the COVID situation is quite serious. Okay, so be very careful. Yeah,
Yes.
you're younger, but then a lot of young people now, the millennials, they also get COVID because maybe they're careless. They go out, go to bars and all those. Okay. So magtiyaga kayo. Ano na yan? Sacrifice for Lent. Okay. So see you Tuesday.
Thank you po, ma'am.
Thank you, ma'am.
Thank you,
Please,
ma'am.
ma'am.
Thank you po.
Okay. Hi, Charles.